I write a compiler for a small imperative language called Elna. The language itself is on the screen, so the compiler is self-hosted and written in itself, but it isn't finished yet, and we can use only a subset of features that are planned for the language. And I always add new stages with new features, and adding new features allows me to use them in the later stages of the compiler. We have one last case where the assignment probably doesn't work, and it is if we assign a field to a variable. And I think that instead of this Elna type field, I test it with a simpler type with this Elna position again. So we actually need two variables. One of them would be Elna location, and another one would be, probably we should edit it in the rake file. So this is the rake file that generates the next stage by copying the previous one and adding some test code. And here we make it to the Elna location, and this one to Elna position. And then I assign the Elna location line and column to different values. And after that, I want to, this is actually wrong. I want to assign y and start location, because it is the value that I want to assign. And then I want to say that x is y start position, and then we print the result. So we are interested to see x line and x column, and probably I should keep the order. So, but I think this is correct. Yes, first line and then column. And these two values are actually enough, I think. Now we can generate the stage 22 and compile it. I think we probably broke the indentation, so I'm going to copy it from here. Okay, and now we can go to the generated assembly. And we see 5 and then some garbage value. So the first field, the first word of the type is assigned properly, but the second word not. The instruction that we are interested in is actually copy from offset, not copy to offset. It's actually called quite a few times. So what is the operand? The first operand is probably the source. The second operand is the offset. And the third operand is the target. Would be actually interesting to see them, or at least into different statements, and we want to see this one, number 3, and actually we can print them in a single statement. And here we probably have our case, copy from offset from Y. This is probably this case, and other two copy from offsets are probably from the printf statement. If I remove this one, then we have only this one. So we copy y with some offset to the variable a1. What is the kind of a1? And probably the kind of the second variable as well, so we can add it here. Okay, both the variables are pseudo variables. I think 4 is pseudo. No, 4 is not pseudo. This is a TAC instruction. So for is a TAC variable. Now we always generate a pseudo from the third operand, but actually we need to do a lookup into the symbol table. So I need an additional variable for that, and then we can copy this lookup, or probably before the printf statement. And in this case, we look up the second operand. The second operand, oh, this is the lot instruction. The second operand is the target, I think. Here we can actually check for the first operand first and see what type is it. So we can actually, let us print the pointer first. We remove the kind lookup again, and we print the pseudo pointer probably at the end or the beginning, at the beginning. So pseudo symbol. Now, as expected, it is always available, always set. so we can access this safely and dereference it and get the operand type. And it has type 2. Type 2 is actually correct, I think. This is an ATL type kind and it is a byte array, which is definitely correct. And if we look for the third argument, for the third operand, then we get 1 here. But this is the 2 second cases, so we get 2 here. So we can actually get, we can actually use the second, the third or the first operand. Both seems to work actually and have the correct type. I probably will go with the third one, and now we go to the ELNA RTL copy to offset, and we just take the handling from here. So pseudo symbol is never nil for now. So let us check for the type. The standard handling is done only if it is a pseudo register. Otherwise, we actually want to generate a memcpy instruction. So first we load the first operand. The first operand is the target. In this case it will be 3. And AD adds an offset, and then we load the second operand to memcpy. And this is actually TSC instruction 1. Let us move this out of the else branch and then use these short variables. And of course we need to generate the instruction itself at the end. And that is actually it. Run operand numbers. Oh, I'm missing the kind. And now it already seems that we have the correct values there. 5 and 3. Exactly 5 and 3 in this order. So this seems to be fine. I actually think that both variables should be pseudomem. Exactly. So we cannot use this tail operand because it also has the wrong type. This one should probably also have a pseudonym here. And not just pseudo. We will test it in a second. So first we need to finish this one. So the case that won't work is if I change this start location to the end location. And here use the end location because we do not add an offset yet. And it is of course the wrong place to change it. We go to the rec file. Exactly. So we need build valid stage 22. And here we have some garbage. So we need just this add immediate instruction, copy from offset, and we put it in here. But no, this is wrong. In this case, we are copying from some variable, so I should add an offset to the source, and the source is in A1. So we change here the register, and the offset itself is in TAC operand 2. So this works now, and we can go to the stage 22, probably just here, and do a quick test where we change the end location again to the start location, just to see that it still works. And this is still 5.3. So now we can remove the debug code, debug output, and go to the rake file again. I want to change this thing once again. So let us put a comment around it. And then we assign these values to X. So we say that X line is 5 and Y column is 3. X column. And then we assign this X to Y, and then we print both X, and actually could add a second printf, but whatever. We just print everything here so that we can see the original values and the copied values. So first we have X, and then we have Y and location line and Y and location column. Exactly 5353. This is the correct values, and I just want to change this one to pseudomem because it is the destination. Yeah, I think it should be a pseudomem. So exactly, the result remains the same, so this is fine. And that means that this feature is implemented now. So the bug code is removed. Yeah. And I have a comment that this was implemented. And before we continue, I want to remove the test stage that I use, so the stage 22, because we will continue to work on the stage 21st for now. And before I do it, or we can do it right away, we can move the stage 22 out of the source tree. And the one thing that we need to do is then to regenerate the Ninja file. It is in the build directory, build Ninja, but here I want to modify the reg file to add some help task to make it with a single command, because it doesn't work currently as I want. And I think that I had a rayclip directory, and it has this file here. So, and we basically have only this task here, but we also have a task for the validation stage, and I use this file here then. Oh, this is the last file that is generated. Okay. So let us define a new task. I probably should define a namespace for this stuff. I don't know, let us call it build. And then we define a task inside it, or probably build is a bad name since I probably use it somewhere. yeah, I kind of have this build directory, and Rake won't able to differentiate between the directory task and a normal task. Should I just call it Ninja? Make probably. Build, since we generate this build file. And what this task will actually do, it will remove this file here. I don't know why I would call it make. So we want to remove this file first, and then we want to invoke the task that generates this file. So basically this one. So let us invoke this task, right, Ninja build. Exactly, that looks good. And now we can just call rake and it will work. And now if I first I add a description for this task. Now if I touch a source file, for example this one, then I can build it. Let us implement the cast operation. This is actually a kind of, this is not a built-in function, this is actually a special operator. So we already have a cast token. Okay, but I do not think that we have an expression for it. And we probably will need a special expression because it is different from the other expressions. So we already have a token kind for it. One thing that we may need is that we can recognize this token. So we have to add it here. So this function basically just tokenizes keywords or reserved words. So now we will need an expression. I think Tokenizer will already generate a token for this stuff. Yeah, I think that we need an expression, Elna-tree expression, and here we have, for example, literals and whatnot. Unary, binary, the reference expression, string literal expression. And we will need a kind for this node, and this kind will be the same as the token kind. And let us define a record probably just after the literals. They actually can move this variable expression after the literals, and then I add an Elna-tree cast expression. It is a record, it has the kind of the tree node, it has type decoration, Elna type, which is set during the type checking, or a pass that will be type checking later, so I do not have a proper type checker yet. Exactly, it has a type decoration, but the type decoration is a different thing. Type decoration is actually type decoration does not belong to the parsing tree, so we need also a different type representation, a variable for the type expression. And I can probably just call it type expression, and its type will be probably just a pointer to Elna-tree node, because I do not have a special node for the type expressions. For example, for the declarations, I have type declaration. Exactly here, for example, type expression and type expression is Elna-tree node, actually the same. as I added here, we can add it with and before we have a type expression, we also have a variable name, or actually not a variable name, but just an expression. I also think that I do not have a special node. I could actually have a special node for expressions. Do I have something like, yeah, I have this ELNA3 expression. Let us actually also add a node type for the type expression, because I use them from time to time. I wonder what do they have in common. So where do we have any ELNA3 declaration? Actually, they do not have anything in common. Therefore, I haven't added it. So its structure will be actually the same as the structure for the normal tree nodes. So this is field types. Pointer type, this is base type. This is actually ELNA3 pointer type expression, so it will be also a type. For the array the same, the base here is the base type of the array, so it will be also I should have called it just ELNA3 type expression. For the traits, that doesn't matter. Then we have these conditionals, and we also have the declarations. Well, that is fine. I was looking at the declarations. Field access expressions. So here we have a type and a tree type declaration. And this word actually should be, so type declaration has a pointer to the next declaration in the list, name at the name length, and the type, and type is actually a type expression. So here we can write the proper type. And we can actually call it type expression. These two have the same structure because this declaration are actually pretty similar. It's almost the same. Yeah, this will break now because we renamed the field. So let us see where it is used. And here we return this type declaration. That means that the type expression is assigned here. And here I get it and I use the type expression from the parser node, and that's it. And now we do the same for the variable declaration. We rename it into the type expression. And it is used here. And it is used here. So this is tree expression list, and to recall, now we can recognize the token. I have a cast expression. And I now need to parse it. It is actually very similar to a function. And function are parsed here. This is parsing for a simple expression, and I actually think that this is the right place. Oh no, this is the designator parser. So this is the simple expression parser, and it parses traits. And if it sees an identifier, so here I parse the thing and then I check that this thing, okay, yes, simple expression is the right place for that. We just add an additional condition here somewhere, I suppose, probably just here, and check whether the token is a cast. If this is the case, then we parse a cast expression, and for that we need to define this procedure. ELNA3 cast expression. The parsing should be pretty similar to a function call, I think. Parser call. So first we declare the result variable. We allocate storage for it. First, we need to skip the cast token itself. We do it with ELNA-Lexa rate. So we move to the next token. The next token in the cast expression will be the open parenthesis. So we can skip it as well. And after that we will have the expression, and we actually can just assign the expression to the expression part. ELNA parser expression, I think. So how do we actually pass a function call parser call? It will parse the arguments. Exactly, here we skip the stuff, and here we parse, for example, an expression, and binary expression is currently the most generic expression, I think. So, and we pass the cursor to it, and after that we need to skip the colon and parse the type expression. So we parse the type expression, and that's it. Then I can return the result, and then we have the parsed expression. So we have a mistake somewhere. This isn't actually a statement, so it does not have a next field, but it has type decoration. And the only thing that the cast expression does is that it changes the type of the expression inside it. So we need to find where the type decoration is set. Will not type capital literal. Will not type simple expression, and if my expression is a cast expression, then we need to handle it here. So else if parser node kind is an ELNA3 cast expression, then ELNA type cast expression parser node. Now we declare this procedure here. It probably returns nothing. And it will set the parser node type decoration to something. Undefined reference to ELNA3 cast expression. Oh, that makes sense. So we need to visit the right hand of the expression, or probably not, because we will overwrite, but we need to type check. We will overwrite the type decoration, but we still need to type check the right hand of this thing. So actually, do I have something like binary expression? Yes, I have. So we will call here ELNA type binary expression, and we will pass the parser node expression to it. And it needs the symbol table. Do I have the symbol table? Yes, I do. So we just need an additional argument to this procedure. Okay, how do I convert a type expression? How do I convert a type expression to the type decoration? So here I take the type from the symbol table. Actually, this is not correct. Type representation is not. So the result is ELNA symbol type info, ELNA symbol type info. Its type is an ELNA type, so the argument will be actually a pointer to the ELNA type. we call this Elna type expression to generate a type and insert it then into the symbol table. Elna name type expression checks what type it is and converts Elna tree node, actually not Elna tree node. We now have this type expression. I think that it gets the type expression. This function is used in the pointer type expression where it parses the base. Here the same for the array, record type expression. To be honest, the most simple solution is just to set the type during the name resolution and not during the type checking. So we will keep this this thing type cast expression, but we will not, because later we will need to type check the expression inside the cast expression, but we will not reset the type declaration. Instead, we will go to the name resolution, to the simple expression as well, but we do not have it somehow. Why? Program body. So our name analysis procedure, the visitor doesn't visit the bodies of the procedures because I kind of didn't need it. I only needed the thing. For the records and things like this, for the types and variable declarations and whatnot. Well, we will do the first test by calling this name, what was it, type expression, by calling it here because we have parser node type expression, and this thing only needs the type expression. So this should actually work. We will move it to the name resolution stage later. I just want to test it. So let us restore the stage 22 now so that I can use this feature. Stage 22. Then we can rebuild the build file, and now if I try to compile it, then it compiles the stage 22. Then we need to update the stage 22 basically by calling rake convert, because it is a copy of the stage 2021, and it still compiles. Okay, now we can go to the stage 22. And we can use the cast expression here and, for example, say that we cast 3 to the type word. Yeah. That looks actually fine. Let's say that y is not a variable in a location and in a position. I think that location is more simple. So position has 2 locations. Let us remove the positions for now. And this is, oh, this code isn't executed at all. No wonder it does work. So once again, we remove this one here and we add cast here. And it doesn't work. Okay, let us go to the rec file, and we want to, oh, it probably doesn't work because printf uses undefined variables. No. Here I just use x line and column. Okay, whatever. We do not need this stuff here. And we do not need this y variable. If I do convert, then it should compile. But it doesn't. Where does it fail? For test view pause, I can just skip tokens. So I know that my current expression is one token and my type expression is also one token. So let us remove the nested function calls and see how we can compile this stuff. I wonder where it actually crashes. So let us see what token is it. We can assign it to the token. Token is a pointer, and that would mean an Alexa token. It has this kind variable, and this is the thing that we want to print. So (32). Left parent. This is actually correct. So if I do the same once again and here assign it to the token, then it should be a colon, I suppose. So we move this stuff here. And it is a colon, which is actually fine as well. Oh, I've forgotten the right parent, of course. A stupid mistake, as always. So actually we just need to skip the right parent, and that should be it. We also will need to adjust the other visitors so that that a visitor can visit the thing in the expression. Basically it should be the TIC visitor, I think. So Okay, now we can compile this thing. At least, here we will add a few comments. This is the parsing. Let us look into our, so we have, I think, a procedure visitor, procedure temporary, procedure temporaries, procedure declaration, exactly. And we will probably have the same thing for the types. The type procedure declaration. And it basically has this ELNA type statements function. So we will define the same thing for the name resolution visitor. So procedure ELNA name statements, and it will almost have the same signature. ELNA type statements. So we get the parser node. I don't know whether we need the symbol table. Probably not. We begin with the parser node. Oh, I need the symbol table for the for this visitor function, I think. What was it? ELNA type cast. Yes, I need a symbol table. No, I don't actually. Because the types are in the global symbol table, I think. So I can resolve the types without local symbol table. Okay, so exactly, we get this node here, and I actually just add a label, so labels start with a dot. And a name statements loop. If parser node is not nil, then Elna name statement parser node, so we handle the first statement, and after that we assign the next statement to the same variable, and we jump to the label. So this is just a basic loop. I haven't implemented loops yet, so I use go-tos basically, and of course the label is wrong. And we do not have this procedure yet, so I declare this one. I think that it has actually this that this one has the same signature. So, and here I add the procedure information to the global symbol table, but I also want to visit statements and not type statements exactly, so I pass the body to it, and we do not need the symbol table for now. So let us quickly check whether it still compiles. Okay. And we will actually need to copy these functions here. Well, they have actually the same signature. I think they just get the parser node, but they know the type of the parser node. So let us define these procedures. So, and we want to rename them. So this is name if, name return, name call, and name assign. Now we can implement this Elna name statement function. We can just add empty functions for some expressions, but not for all of them. And I already, so let us begin with the designator then. And they are actually also all the same. So we will do actually just the same thing, that we copy this stuff and insert it in here, and then we can remove the if blocks. I removed the symbol table argument at the beginning. So this is also the name procedure, And now we can add the type, name simple expression, now Elna type simple expression. Then we have Elna type call. Okay, now we have the types. Name call. Okay, we already have a name call because it is used for statements and and expressions, but we need it only once. Okay, I think that we can now implement this is the functions that are needed for the designator, and I do not have the designator itself, I think. Exactly, this is the things that I needed for the designator. So let us define, let us move it a bit, and then so now we have the designator. What do we need for the binary expressions? For the binary expressions, we need a unary expression visitor. For the unary expression visitor, we visit a designator. And that is kind of it, because unary expression just has just has an expression, a designator, and an operator. But we are not interested in the operator in the name resolution. And here we just copy the type decoration from the nested expression basically. So this one is actually pretty easy. We just define the same stuff. And call the designator but not with the parser node. Oh, there is a difference if it is a unary expression or not. Yeah. Type decoration. Oh, let us update the stage 22. Oops. Now I lost. What was it? Unit expression. Let us update the stage 22 and try to recompile it. Okay, it still compiles for some reason. So the ELNA3 unary expression has this operand thing, and this operand thing is actually an expression, and I have an ELNA3 expression type, I think. ELNA3 expression, and this is the correct type. ELNA3 expression pointer. And if we have this, we can actually remove this unary operand variable, because we can just reference the operand and access the type decoration. Okay, it seems to work. Let us remove this variable. So yeah, and here we will need actually the same. So if we look at unary expression, we will visit the operand here, and otherwise the parser node itself. Now we will do a full test to test that we haven't broken the type visitor, the type checker stub. So okay, And now we can implement a binary expression, because a binary expression will just call to unary expressions. Right. It is here basically. So it assigns binary operand, actually does the same stuff. Parser node is ELNA3 binary expression, and it already has the correct types here. Oops, ELNA type binary expression. Yeah, I won't modify it for now. ELNA3 binary expression. If I say that the parser node is a binary expression, why do I check its kind? Doesn't seem to be correct, but we will keep it for now. I probably should check it in the parent function and not here. So if parser kind binary, then we visit. I visit the RHS first and then LHS. Doesn't look fine as well. Actually, I should compile the left hand side first and not the right. But probably for the type checking it doesn't matter. But still. So otherwise we just call the unary expression here. And we have a binary expression visitor now. So now I can visit the visit statements. I also have empty expressions. Yeah, let us begin with the statements. So ELNA type assign statement. It will be pretty the same here, so we just visit the left side of the assignment and the right side. So now we have the if statements, name if statement, assign statement, call, return statement, and if statement. So the call can be the next, I think. And it actually just visits the arguments, so we can copy it as well. It should be fine. Next. We probably do not need to go to the literals. I actually interested only in the casts. The rest can be skipped. So for the simple expression, I just say that I only want to visit the cast expressions. Yeah, and the cast expression can be already implemented, I think. So the visitor is actually fine. We want to visit and type check the expression inside it. And the same is true here. So we visit with the expression and we convert the type expression and assign it to the type decoration field. and this is of course their own function, but actually should be it. And now we visit the remaining expressions. So let us look into array access. We only need the first part, so we visit the designator of an array and the index that we access, because both of them are the are expressions. So we only need these two first lines for the array access. So base expression is basically parser node array, and this one is index, and that should be it for the array access expressions. And then we have type field access expressions. That looks complicated. What is actually field type access? I mean, array access, array has sub-expressions. Field type access has a designator on the left side before in the front of period. But that is actually it. So everything that I can do is actually visit the aggregate that is accessed, and we do not have a symbol table, so that should be actually enough. And the last one is this, the reference expression. Type the reference expression. And this is actually the same, so only the left side can be visited, so we only need this call here. And that's it. So we call the designator visitor here, and the designator visitor will call the simple expression, and simple expression will then check the cast expression and assign the type decoration is expected. So this is implemented, the cast expression is implemented, and the visitor for the name resolution is extended so that it visits statements and expressions. And that's it then, I would say.